Okay, so solved problems for chapter 41. I'm starting off with the three-dimensional box. We know the three-dimensional box has energy levels as such. What is the degeneracy, or number of different quantum states that have the same energy for a couple different energy levels? So part A, we have a little 3 right out in front there, and the only way for this to happen is if we have nx is equal to 1, and y is equal to 1, and nz is equal to 1. So we only have one state that can meet these energy levels. We're going to add them together, and that's going to give us our 3. And so the degeneracy of this one is just going to be 1. Now, in part B, how do we get a 9 right out there? Well, a couple different states are going to fit this. We could have a nx is equal to 2, and y is equal to 1, and nz is equal to 1. We could also fit this by having nx equal 1, ny is equal to 2, and nz is equal to 1. That would give us a 9 right there. Or we could have 1, 1, and 2. And so this one is going to have a degeneracy of 3. Okay, problem 41.8. First I'm going to cross off some of this stuff. I didn't really talk about the angles, so we're not going to do that. Just want to get a little bit of practice with the relationships between n, L, and ml, and also with the angular momentum and the z component of that. We know that the the angular momentum is going to be related to the quantum number L, where it's going to be equal to L times L plus 1, all multiplied by h bar. And we also know that the z component is going to be related to m sub L multiplied by h bar. And we also know that L is going to be equal to 0, 1, 2, dot, 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 all the way equal to n minus 1. And we also know that m sub L is going to be equal to 0, plus and minus 1, plus and minus 2, dot, 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 all the way up to plus and minus L. So if we have the n equal 5 state, the possible values for L are going to be equal to 0, 1, 2, 3, and 4. The values for L and L sub z, well, let's go ahead and fill these guys out. If L is equal to 0, then we're going to have 0 and 0 inside of this table. For L is equal to 1, we're going to have the square root of 2 multiplied by h bar. We'll just plug those guys in right up there. And the values for L sub z is going to be equal to plus and minus h bar as well as 0. Now for L is equal to 2, we're going to have the square root of 6 multiplied by h bar. And here we're going to have plus and minus 2 h bar, plus and minus h bar, and we're going to have 0 for the z components of this guy. L is equal to 3, we're going to have 2 square roots of 3 multiplied by h bar, and then plus and minus 3 h bar, plus and minus 2 h bar, plus and minus h bar, as well as 0. And last but not least, and our L is equal to 4, I'm going to have 2 square roots of 5 multiplied by h bar. Just did some pulling out for you. And then plus and minus 4 h bar, plus and minus 3 h bar, plus and minus 2 h bar, plus and minus h bar, and 0. Now for problem 17, we have a hydrogen atom in the 3p state. Now the 3 tells us that n is equal to 3, and the p tells us that L is equal to 1. And what we're going to do is going to take a look at some splitting of the energy levels. One thing to kind of keep in mind is if L is equal to 1, that tells us the possible values for m sub L, and that's going to be equal to plus and minus 1 as well as 0. And we're looking at only the interaction of the magnetic dipole moment for this particular instance, so we can just kind of leave spin out of the equation. And what we're going to do is we're going to say that the difference between the energy levels is going to be equal to the Bohr magnetron multiplied by the magnetic field that it is kind of put into. And we're told that the energy difference is 2.71 times 10 to the negative 5th electron volts. And so what does the magnetic field got to be? So technically this also needs to be multiplied by m sub L, but we know the values for m sub L. And actually, let's go ahead and answer part B first. There's going to be 3 energy levels, and they're going to correspond to plus and minus 1 as well as 0. So we're just going to kind of put a 1 in there for right now. So the magnetic field must be equal to the difference between the energy levels divided by the Bohr magnetron. Since it was given in electron volts, I want to use the Bohr magnetron in electron volts. So 2.71 times 10 to the negative fifth divided by 5.79 times 10 to the negative fifth, and that's electron volts per Tesla, and everything works out to be 0.468 Tesla. So now let's go ahead and work kind of a fun little problem where if we were to treat an electron classically, we're going to treat it as just a spherical object with a radius right over here, and we know what type of angular speed we need to produce a spin angular momentum of the square root of 3/4 h bar. So what we're kind of going to do is we're going to say, okay, well, classical physics say that if we have a sphere, that tells us that I is going to be 2/5 mr squared. Hope you didn't forget that. And we also know L is equal to I omega, and we also know that omega is equal to V divided by R. And so now we have all the pieces of the puzzle. So this is going to be equal to 2/5 mr squared multiplied by V divided by R. And so actually we can go ahead and we can cancel out these r's right over here, and we can say, okay, well, let's go ahead and set this equal to the square root of 3/4 h bar. So the square root of 3/4 multiplied by h bar is going to be equal to 2/5 mrv, and v is simply what we're interested in. So v is going to be equal to 5/2 multiplied by the square root of 3/4, 1 divided by m times r. Go ahead and plug all that into your calculator. That's the mass of an electron, that's the radius kind of given above, and we're going to get 2.5 times 10 to the 13th meters per second, and that is much, much, much larger than the speed of light, and so this is actually not a very good model. And last but not least, a little bit with these K-alpha X-rays. We know that it's going to have some energy of 7.46 kilo electron volts. What is it made up of? Well, we do know that the energy is going to be equal to Planck's constant multiplied by the frequency. We can actually get the frequency from Moseley's law that says that this is going to be h multiplied by 2.48 times 10 to the 15th, and then number of protons minus 1 quantity squared. If we were to go ahead and say, okay, well, I've given my energy in kilo electron volts, let's go ahead and plug h in electron volts. So 4.136 times 10 to the negative 15th electron volt seconds. Then what we're going to say is my energy is going to be equal to 10.257 multiplied by z minus 1 quantity squared. I just kind of combined those guys into that number right up there. And since my energy is going to be 7.46 times 10 to the third electron volts, I can say 7.46 times 10 to the third electron volts divided by 10.257 is going to be equal to, go ahead and take the square root of that guy right over there, and that's going to be equal to z minus 1. So you go ahead and you solve this guy, and z is going to work itself out to be 28, and so this is probably most likely going to be nickel, which is atomic number 28.